This conference will now be recorded.
So welcome everyone to another TAP meeting. So just before we start, we wanted to talk about the OCP TAP Tech Day, which is coming in June 2nd. So this is what we have so far aligned for the agenda, and things might change also a little bit. And if you still think like you missed on this and you want to be part of it or something, there's still room. Like if you want to be part of it, let me know or a lot, and then we'll see what we can do with that. And going for our talk today, so it will be by Jeff Sherman from NIST about optical timekeeping efforts at NIST. So Jeff Sherman is a supervisory research physicist at the National Institute of Standards and Technology, NIST, in Boulder, Colorado, part of the U.S. Department of Commerce. Jeff works to maintain and improve NIST systems that produce and distribute official U.S. time interval and frequency signals, which are based on an ensemble of atomic clocks and frequency references. Jeff's research career has centered around high precision measurement in optical atomic systems, includes a Ph.D. In physics from University of Washington, postdoctoral work at the University of Oxford, and National Research Council Research Associateship at NIST. So with no further ado, Jeff, the floor is yours. Let me put you back again as a presenter. Let's see how that works. Jeff, I think you should be able to take over.
My screen sharing button is still disabled.
Okay, let me try it again then. Interesting. Oh, that was another Jeff Sherman. Okay, now.
All right, I believe it's going to work. You should
Great.
see a title slide.
Yes.
My current view, I'm not sure I have a great visibility into the chat box. So
no, this is the right one. And then if anything comes on the chat bot, I'll bring it up for you.
Sure, I don't mind questions during the talk, or I've tried to reserve time for it afterwards. But please, if you feel like immediate clarification, please ask. Thanks for the introduction. Thanks for the invitation. My name is Jeff Sherman. I'm part of the problem here at NIST, Time and Frequency Division. Let's see. Good, we can advance. The Time and Frequency Division fulfills one of NIST's 3 mission essential functions. One of those 3 is to provide official time and frequency sources to the United States, and that's our division's role. We do this both by investing in sort of state-of-the-art, fundamental coherent laser and atomic spectroscopy techniques, and those find their way into applications in complete systems that provide primary and secondary frequency references, absolute atomic references. Those systems calibrate a continuously running ensemble of commercial clocks. What's pictured there in the upper box are hydrogen masers and cesium beam commercial devices. A statistical average of which is steered to approximate the international timescale known as UTC, but it's available in real time as physical signals here and as many places as we can get it. And so another part of the division is to try and disseminate these signals with as high a fidelity as practical for as many sort of use cases as there are. And so for free, but with lower precision and accuracy, NIST operates a radio station in Fort Collins, Colorado that disseminates this atomic time signal via shortwave and ultra long wave 60 kilohertz. That's the WWVB station that powers many quote unquote wall atomic clocks. Also, we run in internet time service disseminating the network time protocol, the request rate has now reached above 1 billion requests per day among just about 25 computers that we run on our premises. We recently started a service to allow customers to bring fiber optics to us, and we may be able to provide formats like PTP or White Rabbit connectivity to the atomic timescale. This is sort of a customer designed service depending on just what a customer is willing to pay to bring a physical connection to NIST. We offer a service that essentially uses the GPS GNSS satellites as a common view transfer standard. So it doesn't depend on the accuracy of GPS, it just depends on the availability of GPS, and you can get UTC NIST remotely as a difference product. And finally, we're beginning a service soon to offer direct site-to-site two-way satellite time transfer. And this is the same thing we've been running for 2 decades as a primary link between UTC NIST and the Bureau of Weights and Measures in France, which operates the International Timescale UTC. This is the primary way that our timescale is compared to the rest of the world. And we're just now beginning to make that available due to demand domestically, prompted by vulnerabilities that are becoming increasingly aware of GPS GNSS systems. But that's not all the division is. We try and make some of these laboratory systems creep forward in technological readiness, and it turns out that precise atomic clocks and coherent laser techniques find their way into lots of applications in fundamental science, sensing, and other fields of metrology. For example, anyone who knows much about the voltage standard based on Josephson junction knows it's effectively a frequency to voltage transducer, and the accurate frequency is then a cornerstone of that apparatus. And some of the most early technological readiness level laboratory experiments push forward sort of the state of the art in coherent phase transfer for ultra precise coherent spectroscopy, integrated microwave techniques, and of course the whole field of trapped ion quantum information processing was born out of trapped ions for clock applications. So we can't talk about everything, but I'll try and review the current state of timekeeping and atomic timekeeping and tell you what's new in the form of optical atomic clocks and frequency references, and we'll mention a few of the applications. I'm sure this audience is familiar with much of the material, so I'm trying to split the difference between enough introduction to bring someone along for the ride who isn't steeped in this, but also maybe a little bit of the latest developments. The broadest possible motivation of this work is that nowhere in nature is a sufficiently good time reference or phase reference. That's just not something that nature gives us. And anything in the sky that you might think of using as such a time or phase reference is either not continuously observable, or it's not stable enough, or it's not practical enough to observe it. So instead, for centuries, it's turned out that the best recipe for timekeeping follows this general idea that one runs a physical man-made oscillator, something that is a periodic regular system, and you just count periods of the system into some unit of time. And to the extent that that man-made periodic oscillator cannot be made, infinitely precise and infinitely universally realizable, you occasionally might compare the oscillator's period to some frequency reference that is given by nature. And to the extent possible, you can apply controls to make your oscillator follow nature's frequency reference and not the man-made mechanical design. So an example that's not quantum at all is you might build a pendulum clock that swings, and you might count the swings into units of time. And to the extent that temperature and the precise length of the oscillator can't be made perfect, you might periodically compare the count of ticks of the pendulum to stars in the sky or the presence of the sun right above Greenwich, England when the clock says noon, and you might decide you're going to trust the position of the sun to be a more stable frequency reference and then apply discipline to the oscillator by either slowly changing its length to affect its frequency, or you might hold it a little bit to give it a change of phase. But we know that the Earth sun rotation system is not infinitely stable. It keeps time at about the millisecond level per day, and the frequency instability of the system is becomes unpredictable after about a year, and that's due to systematic forces like tidal forces will tend over the long term to slow down Earth's rotation rate, but also there's seasonal effects as water moves between the polar regions and the equator. On the other hand, there are stochastic effects like earthquakes that tend to reduce the radius of the Earth, and just like a ice skater pulling in her arms, that tends to speed up rotations. And the point really is this is noise. This is not predictable except in the long term by the systematic tidal effects. The short-term stuff really looks like a random walk in frequency. So Earth as a timekeeping apparatus is inferior at the 9th digit of frequency after about a year of integration. The most sophisticated of pendulum clocks were able to discern this in the 1920s or so. And since then, it's been an exponential increase in quality of this recipe, oscillator and frequency reference. The quartz crystal oscillator started this sort of double exponential gain in timekeeping precision. And then the advent of atomic clocks kept it going. This is a plot that you might think would look better on a log scale until you realize it's already on a log scale and is in some sense a double exponential. And these days we're playing around with laboratory apparatuses that, at least with respect to each other, constrain frequencies at the 18th digit of precision. The SI second as a unit kind of underpins many of the other fundamental units. And as the units were reorganized recently to do away with the artifact kilogram, we now adhere to a general philosophy that units should be based on fundamental, or what are thought to be fundamental, physical constants. And in that sense, the SI second is based on atomic structure, which is not the sort of cleanest fundamental constant like Planck's constant or the electron charge, but is in some sense a complicated linear combination of some fundamental constants of nature. And it just happens that the second is more precisely realizable by many orders of magnitude, like 7 or 8 orders of magnitude more than any other physical constant. And so the other derived units and these fundamental units all depend on the realization of the second. Just to review, there's a network of commercial atomic clocks, mostly commercial atomic clocks, that run continuously, and their observations and physical transmission signals are combined at the Bureau of Weights and Measures in France to make a free-running atomic timescale that has the French acronym EAL. Because it's composed of commercial atomic clocks, it is not assumed to have any fundamental accuracy. And instead, what happens are that a few dozen so-called primary and secondary frequency references, which are based on atoms, calibrates the rate of EAL and creates TAI as a steered offset. What distinguishes a frequency reference from a clock can be blurry, but what I mean is that a clock tends to run completely continuously in phase, with little to no cycle slips, ambiguity of cycle, little to no stopping and starting, whereas a primary frequency reference could be considered more like a tuning fork. You don't ring a tuning fork all the time in an orchestra, but when you do ring it, you hope that it reproduces the same frequency it did last month, and a good one won't depend much on how you hold it, how you ring it, what the temperature is, etc. So I think that's a good analogy to explain what we mean by the difference. And just for completion, TAI and UTC, Coordinated Universal Time, effectively measure the same SI second interval, but they differ by an integer number of seconds. And that difference changes as corrections are introduced called leap seconds, which tries to maintain the rough correspondence of Earth's orientation to UTC. But for the purpose of this talk, they're functionally identical. Why have atoms or quantum systems become the best realized frequency references? Well, I think there are 3 reasons. One, nature seems to produce atoms with absolute identical properties. The tolerances are infinite in nature's factory. the reconfiguration of bound states in an atom, those energy differences that correspond to those reconfigurations of electron shapes or spin orientations are directly related to a frequency by something we think is a fundamental constant, Planck's constant. So any change in energy comes in discrete units that can be identified with a particular frequency. Finally, atoms are dielectric. They're made of charged stuff, and they have magnetic moments, and that means there's two sort of handles on an atom, which you can use to manipulate the state and ring it as a tuning fork, to continue the analogy. But of course, it's a double-edged sword. The fact that the atoms are dielectric means they interact with environmental fields and perturbations, which you don't want. On the other hand, you do want some amount of handles to prepare the atomic state in a particular way, resonantly interact with it to try and tease out what its resonant frequency of transition is, etc. But that's pretty much it. Those are the sort of reasons why atoms have proved to be superior quantum frequency references. And if you just wanted to go shopping, this is a review paper that nicely lays out what commercial atomic clock options there are these days. They vary over size scales and quality, and it's not the case that the least expensive ones are the least quality ones. Sometimes you pay for size, weight, and power and sacrifice quality, but over 2 orders of magnitude between maybe $2,000 and $250,000, these are your commercial options for realized atomic clock frequency references. And that may be enough for most folks. You can tune out and go shopping. But let's talk a little bit more about how they work. I assume that this audience knows a little bit about how passive atomic clocks work. What's pictured here is the earliest attempt at the National Bureau of Standards, which was NIST's former name. This used a molecular transition, a vibrational transition in ammonia. But the recipe is generally the same. You have a physical oscillator oscillating at close to the known atomic or molecular resonance frequency. You tune the oscillator to sit at the peak of absorption, in this case of molecular iodine. And as long as you maintain a servo to keep that oscillator maximally exciting the atom, you believe that the oscillator will then inherit the natural frequency of the vibrational transition, and you count the oscillator. And that's pretty much the recipe for any passive atomic clock, including the cesium beam atomic clock. I do want to maybe talk about an active atomic clock in more detail, because I don't know that in general audiences this is as well known, and the hydrogen maser is still the workhorse of international timekeeping, so it's helpful to know about it. Essentially, molecular hydrogen is dissociated in a glowing tube where there's an RF discharge. You can see it glow. I was born in Las Vegas, Nevada, so this may in fact be why I was drawn to the field. It looks like a neon tube, except it's hydrogen. The discharge plasma makes atomic hydrogen excited. Some of that hydrogen rattles down a sharp magnetic field gradient, which selects the upper two excited states of the ground state of the atomic hydrogen. The other two states are deviated away, so they're sort of differentially pumped out of the high vacuum region. The upper two states, though, go on to rattle around a specially prepared glass bulb at high vacuum, and the bulb is inside of a resonant cavity, resonant at 1420 megahertz, which happens to be the transition between the two MF equals 0 orientations of spin angular momentum. The atoms that go in there are excited, and so spontaneously they may decay back down, and in doing so they emit one of these 1420 megahertz microwave photons with a wavelength of a few centimeters. Normally those photons would go out into infinite space, but the presence of the RF cavity, like an echo chamber, reflects some of the photon energy back resonantly, and that photon energy reflected back can induce a second excited hydrogen atom to stimulatedly emit its excited photon. And now you have 2 photons in the cavity, which could create 4 photons in the cavity. And in fact, it's like a laser, except it's a maser. It's a microwave amplification by stimulated emission radiation. In fact, the maser was the first one before the laser, but the laser is the more well-known version of this amplified technique. And it's a little bit like having a hot microphone where you hold it right next to the speaker. There's an amplification effect. There's a little antenna that dips down into the cavity and couples out about a picowatt of this radiation at 1420 megahertz. And most descriptions of the maser stop here, but I think it's fun to go a little bit further. What do you do with this? How do you count this frequency, and what do you do with all the digits there? What do you really do? Well, this introduces a technique of RF heterodyne mixing, which I want to describe because it sort of clues you in on how this is going to be done for an optical clock. So what we do is we start with a high quality quartz oscillator at 5 megahertz. 5 megahertz is chosen because it's a physical dimension of quartz that can be made very stable and have a very low temperature coefficient or very low dependence on just how you clamp the edges. And then you make essentially a high harmonic of it at 1400 megahertz. Then an RF mixer produces both the sum and the difference frequency, and you can filter out which one you want to keep. In this case, we keep the difference frequency down at 20.405 megahertz. Well, then another harmonic of the 5 megahertz is synthesized into 20.4 megahertz by taking both a harmonic and a subharmonic and mixing those together. And then you mix out that next little bit of frequency, leaving just something at a few kilohertz. Well, that can be digitally synthesized with low error, leaving something at baseband, 0 phase and frequency. And if you feed back that signal to control the quartz oscillator itself, it turns out that you can make the quartz follow the frequency of the hydrogen by a precise division ratio. So it's essentially allowing the 5 megahertz quartz oscillator to inherit the accuracy and precision of the maser, but at a standard tone, a standard frequency, which, for example, if you just counted 0 crossings, 5 million of them, you would then make an SI second according to this hydrogen clock. These things ship from the factory with frequency inaccuracy in the 12th digit. It's really down to collisional effects. They tend to drift mostly linearly, about a part in 10 to the 15 per day. They have a temperature coefficient of about a part in 10 to the 14 per degree C, and a humidity coefficient that's of order 10 to the minus 15 per % relative humidity. So at NIST, we try and operate these things in very high performance environmental control chambers that try and control the temperature at 0.1 centigrade and the humidity at about 1%. These things tend to have a lifetime of about 20 years where they really do operate phase continuously for as long as the power is on. Our experience is that they're complicated systems inside, and they experience maybe one major failure in that 20 years that require wrenches and diagnostics and real fixing. This frequency instability that's shown translates into a predictable time output of one of these clocks at the level of about 100 or 200 picoseconds per day. The blue series is the raw data difference between 2 of our best performing hydrogen masers at NIST. The orange data removes the linear drift component. And you can see that if you allow yourself to discount the linear drift as a predictable component, these things play around in the few parts in 10 to the 16 level of stability. Because we don't want to depend on just one of these clocks to power our output, what we actually do is run about 20 clocks in an ensemble sense, where the phase differences of any pair of clocks is continuously measured and known. And then a synthesizer offset is applied to one of the clocks, correcting for its phase and frequency, such that the output of the synthesizer is in phase and frequency agreement with the rest of the world. We call that output UTC NIST. We call the algorithm that does this phase and frequency ensemble averaging AT1. And its property is it tries to predict which clocks appear the most stable with respect to the average, and it gives those clocks more weight in the statistical average. It administratively limits how much weight any particular clock can have, because we don't want to give all the weight to a healthy clock that suddenly could become unhealthy due to a technical failure. UTC NIST is a signal that is broadcast, for example, by two-way satellite time transfer transatlantically. And then we receive updates every week and every month about its relative performance. So this, for example, the orange is weekly data we get. The weekly data is known to be more noisy and unofficial. The official data of difference between our timescale and the official timescale UTC is shown in blue, but you have to understand that we get this data a month after the fact. So our job is to try and keep this quantity small, but we only have last month's data to predict what systematic biases UTC NIST is currently experiencing. This is a statistical measure of time predictability. And what's shown in colored lines are various commercial atomic clocks or a model of a noiseless atomic clock that just happens to have a part in 10 to the 15 offset mysteriously in red. And the data there is showing the performance of UTC NIST versus that unofficial weekly series, UTC Rapid as it's known. And it shows that we hold basically about a nanosecond over periods from 1 week to about a month. That is essentially our servo time constant for how quickly we tend to make steering decisions. I don't want to dwell too much about this because we just published a lot of details, more detail than really had ever been made available in this technical note. So you can read to your heart's content about all the redundancy, reliability, the multiple measurement systems, and sort of the nuts and bolts about what makes the ensemble work. In summary, it's less physics and it's more chaos management. We run an awful lot of uninterruptible power supplies, 2 dedicated diesel generators on dedicated circuits. The clocks all have their own independent battery backup, which I cycle every 2 years. All of our rooms, which are spread between 2 buildings, have redundant cooling methods. The clocks, as I mentioned, have their own independent cooling chambers within these rooms. And we try and measure every clock multiple times with different systems. We send clock signals between buildings and measure them in 2 different buildings. We try and keep the primary data systems off the general network. We try and write code, for example, that relies on 0 external libraries. All the analysis is done then using the great benefit of libraries and analysis tools, but it's done on the general network after the data has been collected and stored redundantly. So that's the live system. The live system is based on these commercial atomic clocks, and in principle, the live system is calibratable by NIST's absolute frequency reference. The one shown here is NIST F2. It's the cryogenic cesium fountain, which attempts to realize the definition of the second, which is in terms of the ground state hyperfine splitting transition in atomic cesium. Cold cesium atoms are prepared at about 1 microkelvin in an optical molasses, and then a final pulse of light gives them momentum, sending them up into this drift tube apparatus where they pass through a microwave resonant cavity where 9.192 gigahertz microwaves are introduced. Those microwaves are tied to the NIST timescale, so if the NIST timescale has an offset, they will be realized as an offset with respect to the cesium atom transition frequency here. The atoms fly through the cavity on the way up, and they fall through the cavity on the way down. This is a spectroscopy technique designed to eliminate many motional systematic effects and others you could think of. The design of the cavity is incredibly complicated, and I don't have time to go into it here, but the resulting spectroscopy signal is shown there on the right. The idea is that you want to keep the microwaves tuned such that you're exciting the central peak, which is discernible there at 0 hertz on the bottom right slide. And a servo mechanism is done to sort of track what the drift and absolute offset of the frequency of the microwaves is with respect to the atoms. So what's next? I've hinted that currently the state of the art is to transition to not microwave, but optically based atomic clocks. Why would you want to do that? All else being equal, and it never is, but if all else were equal, a higher frequency is inarguably better. And I want to describe why. There are 3 reasons. 1, because you're using a population of independent quantum absorbers, n atoms in this proportionality equation, it turns out that there's a limit, a shot noise limit, because you're observing a finite number of atoms for a finite amount of time tau. There's sort of a limit of how much frequency information one can tease out of them. And given that you have to prepare these atoms, and then you might be able to probe them for, let's say, 1 second of coherent spectroscopy, well, that corresponds to an uncertainty of the upper state energy of about 1/1 second, or 1 hertz. This is known as the time energy uncertainty principle. So that delta F will always be about 1 hertz for a microwave clock or an optical clock if you can only observe atoms coherently for 1 second at a time. Well, then it behooves you to have a large denominator F to make that the relative size of 1 hertz very small. And an optical frequency can be 100,000 times faster than a microwave frequency. So if you can, you get a more stable clock by making F bigger. Second, there are some systematic effects, perturbations due to the environment, some whose absolute size is independent of F, and then the relative effect of it is proportional to 1/F, and therefore you want a bigger frequency. One example is the linear Zeeman effect, which is the effect of magnetic field on an unpaired electron spin, for example. That tends to be about the same size, whether we're talking about an optical clock or a microwave clock, because a spin is a spin, more or less. So that effect is just much smaller, relatively speaking, in an optical clock, because you get to divide that shift by a bigger F. Now, not all systematic effects scale this way. Motional effects do not. It turns out that black body radiation of room temperature does not. The relativistic gravitational shifts do not. But, for example, there is essentially no magnetic shielding needed in much of the optical clock work that's around here, but very serious 4 and 5 layer magnetic shielding needed for the microwave clocks, just for this reason. Okay, and finally, the reason faster is better is if you just imagine that you're going to be counting an oscillation into intervals of time, well, it's just much better if you have more oscillations per unit of time. If all you had was enough signal to noise to discern 0 crossings and nothing else, then every wave of an optical wave passes over you with femtosecond intervals. So if all you can do is count digitally cycles, you'll be doing thousands of times better optically than you would counting a microwave, which passes over you 1 wave every nanosecond, just for example. How you actually count this will come up later. It's much more difficult to count cycles of an optical wave. It required a Nobel Prize winning invention called the optical frequency comb. And it's plotted here to show that it was really with the advent of that device, the frequency comb, that interest and progress in optical standards, shown here in red, really surpassed or began a steep slope of progress compared to the microwave standards, the best ones known, which are the cesium fountain atomic clock shown in blue. We're now in an uncomfortable situation where the optical secondary references are known to be better performing by about a factor of 100 in both stability and accuracy than the thing that defines the SI second. So there's talk about redefining the unit. What makes up an optical clock are really 3 components. One has to stabilize a laser to Hertz level or better, just so that one can usefully interrogate a narrow atomic reference. So that's the second piece, is some atomic reference. And then the third piece is this device called a femtosecond laser frequency comb, which you could think of as a set of gears with a ratio of like 10 to the 5 that coherently links some optical wave to a microwave, and the microwave is slow enough that it could be counted by mere electronics. So we'll talk about each of these pieces just a little bit. Starting with the optical reference, the atomic optical reference, there's really 2 technologies that have proven viable at the part 10 to the 18 level. One is a technique to charge an atom by knocking off an electron that's then called an ion. And the ion's charged, and so it can be confined by very careful arrangement of electric fields. You can actually confine just a single ion this way, and by cooling it, you actually cause it to emit fluorescence, and by the fluorescence, you can know its atomic state, and you can manipulate its atomic state. The ion techniques have possibly lower systematic biases just because it's a simpler system. It's a single atom, and the way you trap it by charge is kind of decoupled from its internal structure. On the other hand, it turns out that you never really can trap the ion at absolute rest without some residual motion driven by the trap itself. And that contributes a relativistic shift that has to be studied as you do the clock spectroscopy itself. So if anything was an Achilles heel of this technology, it's the motional effects. On the right is a depiction of a technique for neutral atoms. So they stay neutral, we don't knock a charge off. Instead, the neutral atoms are confined in a focused retroreflected light called an optical lattice. It's called an optical lattice because by retroreflecting the light, you make standing waves, and the atoms tend to fall into high field regions of the standing wave. So it's a crystal structure in one dimension, hence the name lattice. You can trap and interrogate tens of thousands of atoms at once this way, but the details of the trapping are more complicated, and it's more difficult to tune the trap so it doesn't influence the internal atomic structure of the atom and perturb the clock. So if this technique had an Achilles heel, it's that the details of the trap are highly difficult, and quite a lot of work goes into designing and maintaining the optical lattice. This is a picture of one, the ytterbium optical lattice at NIST. The photograph was taken by waving a white card around on a long exposure, and so you can see the laser beams. The red color is the detuned, retroreflected optical lattice before it gets sent into the vacuum system. And the yellow color is what we think of as the optical clock. This is an instrument that measures the frequency of yellow light, because it turns out that this color of yellow is resonant with a very weak isolated transition within the ytterbium atom. When we made this absolute frequency measurement, we did so at the 16th digit, but the major contribution to the uncertainty is actually in the unit of hertz. The realization of the SI second is only as good as the performance of the cesium fountains, and averaged over 8 months, that performance was about 2 parts in 10 to the 16. Most of the other uncertainties due to the optical side are an order of magnitude or 2 lower. What's shown in the inset is the dramatic atomic response. If you tune the yellow light by just 1 hertz out of 518 terahertz, you see essentially a unitary contrast of absorption signal in the system. To really show you, this is what it looks like in the lab. You can see, for example, the cooled magneto-optical trap of ytterbium atoms using this strong blue transition. It refrigerates by fluorescence, and you can see the fluorescence, and this is what that looks like. This brings the atoms to about 1 millikelvin temperature. To get them much colder, we use a slightly weaker transition at this green color, but it's strong enough to fluoresce. You can see it, that bright dot in the middle really is about 100,000 fluorescing ytterbium atoms. This is a CCD camera image, not how the trap is actually run. The green magneto-optical trap was still on and is responsible for the diffuse cloud there of green, but the trapping light is on, and that produces that high intensity red-white pixels. That's a dense collection of atoms still fluorescing in the green. In the real clock operation, we wouldn't leave the fluorescing atoms on to fluoresce during the clock, but this is just to illustrate the coldest ones falling into the optical dipole trap. Once they're in there, we turn off all the lights except for the dipole trap that creates these many, many lattice sites where between 10 and 20 atoms live at finite temperature. And then we turn on this resonant light at a yellow color, 578 nanometers. And after that, some of the atoms are in the ground state, some of the atoms are in this excited state labeled 3p0, and then an experiment is done to ask how many are excited. If you scan this yellow light over a very large range, you can see a strong so-called carrier transition at the free, unmoving resonance frequency, but then all the motional effects are pushed out into side bands. This is because the atoms are trapped to a region smaller than a wavelength of light, which turns out, it's known in the business as the Lamb-Dickey condition. It's true, by the way, for hydrogen masers. They're confined to a bulb that's about the size of the wavelength of light, and it's the same reason you get narrowing in that microwave cavity. Well, here we have the atoms trapped in half wavelengths of standing wave light, which is of the order of 578 nanometers. So you get the same narrowing effect. The motional effects are pushed out, and in fact, the asymmetry you can see is a function of temperature. So you can know the final temperature of the atoms, which is about 10 microkelvin, by measuring the asymmetry in these sidebands. If you zoom right in on that carrier, you find that it's as narrow as you care to look. Here, the atoms were excited by the yellow light for about a second, and that time on energy uncertainty principle means that you see a Fourier limited line width of about 1 Hertz in that central feature. So the game is to run this not in a scan mode, but in some kind of servo mode that keeps the yellow laser centered around the peak of this transition, and by doing so, the yellow light inherits the stability of this atomic response. This is what data really looks like. We've had 2 of these apparatus fed by the same yellow light, and the difference between each is shown in the upper red-black plot. The fact that they trace each other means that they see the same variations in the laser, which is a few hertz over this day or so of running. And then the difference signal shows you really what the stability signal is like between these 2 systems. This is raw data from the first clock, I think, which showed stability in the 10 to the minus 18 region. The other branch of technology that reaches this is the so-called trapped ion. And here I show one early work that's under active development at MIT Lincoln Lab, using tightly integrated photonics that bring all the lasers in needed for state manipulation. And the clock interrogation here is at this red color, 674 nanometers. Well, all those lasers are brought in to this photonic chip, which also serves as the electrical potential needed to trap the ion about 50 microns above the surface. It turns out that an ion trapped so close to a surface is subject to a lot of thermomechanical noise. So the whole thing has to be strapped to a cryogenic cold finger to reduce that coupling. As I say, this is an early stage work, but it shows that the process could be highly integrated and doesn't necessarily have to consume an entire lab of free optics, maybe just a quarter of a lab or so. That's one of the 3 things you need to make this work. But the second one is you got to be able to count the laser oscillations. And how do you do that? Well, if it was last century, you built an enormous frequency multiplier chain all the way from the microwave standards, the masers, and maybe the cesium fountain, step by step, factors of 2, 3, and 10, all the way up to the optical. And each of these lasers would sort of bridge the gap. This was incredibly complicated, and it had to be tuned for any particular optical transition you might look at. Instead, what was really needed is some kind of coherent technique that would link a microwave frequency to lots and lots of optical frequencies by high harmonic generation. And effectively, that's what was produced. The femtosecond laser frequency comb is a pulsed laser, but it's special in the sense that the pulse is composed of many tens of thousands of coherent continuous wave modes in the laser, such that coherently they add up to what looks like a pulse on the outside of the cavity. But you could think of the carrier underneath the pulse is coherent between pulse 1 and pulse 2 and pulse 3. One way to understand this is that every optical mode in the cavity is essentially a high harmonic of the repetition rate, the rate at which the pulse bounces back and forth in the cavity. It's like every optical mode is a large integer n, where the n is like 100,000 of the repetition rate, with one complication, that the whole forest of high harmonics is offset by a constant frequency offset known as f0. It turns out that f0 is measurable. I don't want to get into how and why, but you separately measure it. You can measure the repetition rate, and you can measure the heterodyne beat frequency of, say, the yellow light from the ytterbium clock and the nearest yellow comb tooth or high harmonic of the repetition rate f sub r. You can calculate what the integer n must be, and then you can relate the repetition rate, which is a microwave frequency, like a gigahertz, to the unknown but definable F clock up at hundreds and hundreds of terahertz. So this is the coherent divider. And then you count the repetition rate with the same fidelity that the clock laser has up at an optical frequency. So this was the whirlwind introduction. To go even faster, I'll say that it's only in the last few years that we have demonstrated this instrument works to create microwaves with instabilities down in the part and 10 to the 18s. And anyone looking for details, I recommend the supplemental material for this paper. It turns out there's a fantastic amount of technical complications involved in just the microwave synthesis, software-defined radio techniques needed to span arbitrary frequencies, the choice of photodiode where you run the pulses into. The technical mountain is enormous, and lots of effects had to be tightly controlled and understood. What this work demonstrated is that two optical clocks compared optically by direct heterodyne gave the same answer as the two optical clocks divided into 10 gigahertz microwaves and then compared in the microwave domain. So whatever the clock noises were faithfully replicated down in the microwaves at sub-femtosecond level stabilities. These femtosecond laser frequency combs are a commercial component, so these are no longer things that have to be sort of fabricated at labs like ours. I think that's where I want to leave the discussion of the comb. The sort of final technical component here is some way to create a so-called local oscillator or pre-stabilized laser of sufficient quality to be able to see a 1 hertz kind of line width in atomic spectroscopy. So there's some analogy here between the workhorse of microwave oscillators, the quartz crystal oscillator, and these exquisite, essentially length references, where the mechanical object separates two high reflectivity mirrors, creating an optical resonant cavity. A laser made resonance with this cavity essentially inherits the length stability of the cavity. And then lots and lots and lots of engineering choices go into making these cavities robust in length. For example, you choose a material with a very high stiffness or Young's modulus and low loss tangent for acoustic modes. There are component glasses, fused silica, sapphire crystal, and silicon are good candidate materials. And as I say, the material is just there to separate two high reflectivity mirrors, where the reflectivity is such that photons bounce maybe 100 or 200,000 times before being absorbed by the cavity. So there's a high amount of coherence in the stored light. It sort of averages over the frequency over the last many milliseconds. So it's sort of like an ultimate delay line stabilization technique. You might think of it that way. The material is chosen so that at some temperature there is zero linear coefficient of thermal expansion. Here's one in silicon. There's actually two such transitions. If you're willing to go to ultra low, sort of 7 Kelvin, or the mid-range 120 Kelvin regime, there are zero crossings of this material. Ordinary fused silica, depending on how you dope it, has a zero crossing at cold temperatures. And if you highly dope it, it becomes a commercial glass called ultra low expansion glass that can be made to have a zero crossing closer to room temperature. But that's not it. One really needs to stabilize the temperature at this glass or silicon object. For example, if it's at room temperature, the stability over 1 second intervals has to be 10 nanokelvin. And you do that by having a high amount of blackbody radiation, shielding, and passive isolation to the environment. You have to put this thing on vibration isolation platforms and design the shape such that vibrations don't couple into length changes. And body loading and orientation changes shouldn't change the shape either in a way that changes the length between the mirrors. But one with all these technical achievements, one can achieve an oscillator with a short-term stability of a part in 10 to the 16. And essentially then you're holding on to how good you can control the temperature and other environmental factors It only has to be controlled long enough to usefully use this oscillator to interrogate an atomic reference, which has no intrinsic sensitivity to things like room temperature and vibration, or at least that's the idea. So just to skip to sort of what the ultimate idea is one of these objects fabricated across the street at the University of Colorado exhibited better than hydrogen maser stability out to periods like 2 or 3 or maybe 4 days. So the idea is one could use this oscillator all on its own as an optical time generator if you compared it to an atomic reference every day, every other day, or maybe every 3 days. And so that's what was done. It was left as a free-running oscillator overnight, but then most days in a 34-day period, they fired up the strontium optical lattice clock experiment to essentially recalibrate what the length or what the frequency of this oscillator was. And although there was no physical signal disseminated, we could sort of use a common filter model to estimate how much integrated time error this sort of ersatz optical timescale would have produced. And it's of the level of 100 picoseconds of error integrated over a month, which is about the level of international timekeeping generally. Just for this audience, I wanted to point out that there are some vastly simpler schemes that don't need an optical cavity and can directly interrogate a laser and an atom or molecular reference. This is probably commercializable. This is a molecular spectroscopy of iodine. It has a resonance frequency in the green somewhere. And so a laser is directly stabilized to this gas in a cell. And this mount looks kind of funny, but it's an optical contacting method of optics on glass, which is space qualified. It's extremely stiff and stable, which is why it's used. And the plot on the right shows that all by itself, this object can produce stable frequencies at the few parts in 10 to the 15 level out to several hours without a fantastic optical cavity and without one of these laboratory-sized optical lattice or trapped ion standards. So it's got a path to commercialization and miniaturization. Similarly, this is a 2-photon transition optical in atomic rubidium. Rubidium is used as a vapor in several microwave clocks. And the physics package isn't all that different. This is a cell full of rubidium vapor, but it's just interrogated optically with no stabilization cavities because the atoms can be interrogated at sufficiently high signal to noise. It's a 2-photon transition to remove Doppler effects. The 2 photons are introduced with counterpropagating K-vectors, and it's sort of an ideal experiment. It's pumped in the infrared, but you look for fluorescence at a blue color. This is realized a few parts in 10 to the 15 stability out at several hours. It has worse drift character, really probably dependent on the light shifts induced by these infrared lasers, but also the simplicity of this package makes me think that it's much more commercializable than the ultimate laboratory references we discussed. Okay, so finally, I mean, what are the applications for all this besides ultra-precise timekeeping? Well, very long baseline radio telescopes really do need better clocks than hydrogen masers, especially as they push their radio carriers up into the 10 and 100 gigahertz regime. The inverse of VLBI is sort of beyond 5G, massive, multiple input, multiple output, where the idea is antennas designed to communicate with cell phones spaced across a city, if they were emitting coherently, can design waveforms to boost the signal to one user while attenuating it for another. In other words, make better use of bandwidth. And these could benefit by some of these optical frequency references. In fact, an optical frequency might be the best way to make millimeter wave or terahertz wave coherent oscillators. The femtosecond frequency combs have a whole forest of applications. The fact that they can produce a coherent wideband emission makes them good for trace gas sensing and attosecond science. You can really image the response of wave functions using the pulsed laser. There's fundamental science applications. It turns out that ratios of these clock frequencies, if they are stable, they constrain what fundamental frequency fundamental constants of nature might be drifting. So here, for example, shows the constraints on the so-called fine structure constant and the mass ratio of the proton to electron. And the more measurements you make, the tighter these constraints get. The plot on the left has been made 2 orders of magnitude better by the recent paper on the right. So these constants are now known to be constants at the level of parts in 10 to the 18 per year. You also can make atomic clocks into ultra-low wave gravitational wave detectors or sensors of certain classes of dark matter. This is a paper from a recent result run in Boulder. 3 of our clocks were run, and just the lack of fluctuations in their ratio constrained certain speculative scalar dark models where you sort of know how much dark matter there must be to explain gravitational rotation curves, but what's not known is the mass of the scalar particle and their coupling constant with matter. But because you don't see fluctuations of the clock ratios and the clocks are known to have differential coupling, one can write down constraints for just what kind of dark matter particle there might be. So this isn't a detection, but it extends the exclusion regime, sort of rules out models. Finally, you may know that the gravitational redshift makes clocks into elevation sensors close to Earth's surface. The clock frequency changes by a part in 10 to the 18 for every centimeter displaced from Earth's surface. This was first observed at this level of precision here at NIST when James Chow down the hall literally got a car jack and lifted one of the optical tables up by about a foot. And they saw the frequency difference between 2 ion-trapped based clocks change at the part in 10 to the 17 level. The result's been repeated in a more robust way where an optical clock has been transported up into the Alps near the National Lab in Torino. And more recently, a portable system has been created in Tokyo by Professor Katori, where he lifted one up into the Tokyo Tower. So this demonstrates that the clocks are getting robust enough to leave the lab and be hoisted up an elevator. And here you can see the spectroscopy signal shifted by 21 hertz, which is exactly what you'd predict by the gravitational redshift, just as a demonstration experiment. Okay, so that about wraps up the material. I'm happy to answer questions. You've heard a little bit about timekeeping as it is here at the National Institute. I hope I've shown you a little bit about the upcoming optical atomic clocks and frequency references and talked a little bit about the applications. And I can't emphasize enough that I'm summarizing the work of lots and lots of my colleagues here, not just myself. Anyway, thank you again for your attention. Happy to answer questions. Cheers, thank you.
Thank you, Jeff. What a wonderful presentation. So, quick question: is it fair to say that ultimately, like all these physical like phenomena, whatever we use for time, like for frequency, like stability and everything, they're filters. They're bandpass filters that are super sharp, like due to like driven by some, like again, you said that what nature really gives us a lot of precision in is the structure of atoms. So is that fair to say like we're always looking for a bandpass filter?
I think that's a fair way to say it. I like to say that the frequency references are like tuning forks. You want them not to run continuously, but they're designed to be insensitive to how you hold it, what the temperature is, whether there's a magnetic field. I mean, that's what makes a good tuning fork a tuning fork, is you can rely on it to, be the same oscillator a month ago as it is today. There's a separate idea that if you need to continuously make a periodic system, make a live signal, well, then you wouldn't really wrap a tuning fork over and over and over. So those are engineering differences, but they both share a sentiment of what you said in that they both sort of have an active response that's essentially as infinitely narrow as one can engineer it. That's right.
There's a question from David Chandler. David, do you want to ask the question directly, or I can ask it for you?
Yeah, sure. I'll be.
Go ahead, David.
Yeah, Jeff. The iodine and rubidium small clocks that you showed up there, the 8F plots had things like the drift and the quadratic removed. Is there anything in those papers indicating what those numbers would be, like what the daily drift actually is on those when that information's not removed?
Yes, I'm sure it's in the paper. I don't remember it. I don't
Okay.
have it there.
All right, I'll look up the reference. Thanks.
Cheers.
Any more questions? One more question, Jeff. Like, how far are we, let's say, to look? I mean, again, this more on Bohr's model. Let's say, and I mean, there is also the uncertainty, and then when we do measurement, we interrupt whatever it's going on. Looking at, like, let's say, different frontiers, like in the atomic structure. Let's say, for example, I don't know, rotation around or orbit of an atom around things like that. Like, how far are we from those things, or are we going toward those things?
If I understand the question, it's not the case that there are theorists predicting the frequencies of these atoms and then we go test it. The theory, although we think we understand quantum electrodynamics, is not yet possible to compute at 18 digits. The theorists, the best they can do for very particular atoms is like 0.1%, or in heroic cases, maybe 0.01%. So it's not the case that we'll ever sort of test theory directly by measuring an atomic frequency. Instead, the sort of ansatz is that the atoms kick out proper time that's related to essentially an arbitrarily stable, universal, quantum mechanical Hamiltonian. And to the best of our ability, we might engineer our oscillator to mimic the transition frequency of the Hamiltonian. What can be predicted at high precision is the sensitivity of clock ratios, because just for example, an optical transition is more sensitive to the fine structure constant than a microwave transition, just because the thing that makes a microwave transition go is really a magnetic field strength within the atom, and the thing that makes an optical clock go is really a reorganization of the electron's shape. So they're sensitive to different physical phenomena, and it is possible to predict the differential sensitivity to other fields like dark matter fields, like changing fundamental constants, like remnants of inflationary physics. And there, if you detect anything at all, it's revolutionary. And nobody really cares yet about detecting at 10% or 1%. It's really detecting any kind of response. It would be a major victory. So that's the frontier of testing theory. And it's not the case that the absolute value of the frequency matters to anyone, because nobody can compute it. Does that?
And then the increase of a universal, like, entropy, that is probably also going to reflect in that, right?
I guess I don't think so.
No.
So there is, as I understand it, and I'm not a specialist, is that universal inflation is at a large distance phenomenon, and bound systems like atoms sort of slip through the inflationary part of space-time. And it's not like the hydrogen atom is expected to inflate with inflation. It's a quantum mechanical bound system, and it's not subject to the change in the metric that inflation is driving. The quantum mechanical bound system is sort of separable physics. That's how I understand it as a non-specialist. On the other hand, emissions from an optical clock or any atomic emission propagates through the universe forever. And so, for example, periodic systems like quasars have a fast rotation rate and they emit pulses. Those pulses may take millions or maybe a billion light years to get to us. And in the process, they spend time traversing an inflationary metric. They pick up low frequency gravitational waves and other perturbations on inflationary physics. So there is a program to detect fluctuations of a pulsar in that part of the sky against a pulsar in that part of the sky, and look at the power spectrum of apparent noise in the universe to try and discern this kind of inflationary space-time physics. That is an active program, but you see how that's different because it's not a bound state in space anymore. It's a coordinate sort of broadcast of a frequency that traverses across the physics of interest. You could think of it that way.
But the increase of entropy, I meant more like increase of the floor noise in general, because you're
Well,
constantly fighting against that one.
As far as we know, atoms, they don't have like a spring in them that runs down. They don't run out of batteries. They are unitary systems that are the same today as they were yesterday. They experience, the internal state of the atom experiences no entropy. The open quantum system that we all live in, where photons are exchanged, of course, experiences entropy. But when we run the clocks, we don't have to use the same atoms time after time after time. In fact, load different atoms every time we run the apparatus, but it's expected that the atoms are identical. So we remove ourselves from the macroscopic entropy, if you like.
That's beautiful. Any more question? We run out of time. It's so amazing presentation. With no, I'm enjoying it. Any more questions for the audience?
Thanks, Jeff. Really great stuff.
Doing good.
Cheers. Well, we in our group are following with interest the time appliance, and we're interested to even discover this group meeting. I'm curious to hear more about your projects, and thank you again for the invitation.
Welcome. Thank you very much, Jeff.
Thank you.
Right.
All right,
Okay, bye,
signing
everyone.
off. Take care.
See ya.
Thanks, Jeff.
Thank you.